Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Mars beckons to humanity as our cosmic neighbor, a world that once flowed with rivers and harbored vast oceans billions of years ago. Today, however, the red planet presents one of the most formidable challenges our species has ever contemplated, transforming an entire world to sustain human life. The question isn't whether we should terraform Mars, but whether our current technology could actually accomplish this monumental task. Standing on Mars today, an unprotected human would face immediate death. The atmosphere consists of 96% carbon dioxide, with virtually no oxygen, creating surface pressures less than 1% of Earth's. Temperatures plummet to minus 125 degrees Fahrenheit at the poles, while even equatorial summers barely reach 70 degrees Fahrenheit. The thin atmosphere provides no protection from deadly cosmic radiation or solar particles that would quickly destroy human DNA. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. Yet Mars possesses crucial advantages that make it our solar system's most viable terraforming candidate. The planet experiences 24-hour and 37-minute days, remarkably similar to Earth's rhythm. Seasonal variations exist due to Mars' 25-degree axial tilt, creating familiar weather patterns. Most importantly, substantial water ice deposits exist at both polar caps and throughout the subsurface, providing the fundamental ingredient for any terraforming attempt. Current robotic missions have revealed that Mars contains all essential elements for supporting life. The Curiosity and Perseverance rovers have detected organic compounds, methane plumes, and mineral formations that suggest past habitable conditions. The Mars Reconnaissance Orbiter has mapped extensive subsurface ice deposits, while the InSight lander has revealed the planet's internal structure and seismic activity. NASA's current Mars exploration timeline envisions human missions by the 2030s, establishing permanent research stations that could serve as terraforming foundations. SpaceX's Starship development program aims to transport 100 tons of cargo per mission, potentially enabling large-scale infrastructure deployment. These missions represent humanity's first steps toward planetary engineering on an unprecedented scale. The engineering challenges are staggering. Mars has lost most of its original atmosphere to space over billions of years, stripped away by solar wind due to the planet's weak magnetic field. The remaining atmosphere cannot retain sufficient heat or pressure for liquid water to exist stably on the surface. Toxic perchlorates contaminate Martian soil, making it lethal to most Earth organisms. Despite these obstacles, several terraforming approaches have emerged from serious scientific study. Atmospheric thickening through greenhouse gas release could gradually warm the planet and increase surface pressure. Magnetic field generation might protect a developing atmosphere from solar wind erosion. Biological introduction of carefully selected microorganisms could begin transforming soil chemistry and atmospheric composition. The timeline for Mars terraforming spans centuries or millennia, depending on the methods employed and resources committed. However, recent technological advances in genetic engineering, atmospheric chemistry, and space transportation have accelerated what once seemed impossible. Private space companies now invest billions in Mars colonization technologies, while international space agencies coordinate unprecedented exploration missions. Understanding whether current technology could terraform Mars requires examining each aspect of planetary engineering: atmospheric modification, magnetic field generation, water cycle establishment, soil remediation, and ecosystem development. Each presents unique challenges that push the boundaries of human capability and ingenuity. Transforming Mars' razor-thin atmosphere into something capable of sustaining human life represents perhaps the most daunting aspect of planetary terraforming. The current atmospheric pressure of 6 millibars, less than 1% of Earth's sea level pressure, cannot support liquid water or protect against radiation. Yet scientists have identified several approaches using current and near-future technologies that could dramatically thicken Mars' atmosphere over geological timescales. The most promising atmospheric engineering strategy involves releasing massive quantities of carbon dioxide currently locked in Mars's polar ice caps and subsurface deposits. The southern polar cap alone contains enough frozen carbon dioxide to increase atmospheric pressure by 50% if completely sublimated. Targeted heating using orbital mirrors, nuclear reactors, or even controlled asteroid impacts could trigger rapid CO2 release, creating a runaway greenhouse effect that would continue warming the planet. Current technology offers several methods for atmospheric thickening. Solar concentrators using lightweight mirrors could focus sunlight on polar regions, gradually sublimating ice deposits. NASA has studied using nuclear thermal rockets to deliver heating elements directly to polar caps, more dramatically, redirecting. Small asteroids to impact polar regions could release enormous quantities of greenhouse gases while adding valuable volatiles to the atmosphere. Methane production presents another viable pathway using existing biotechnology. Methanogenic bacteria, already used in Earth-based waste treatment facilities, could theoretically survive in Martian conditions with proper protection. These microorganisms convert carbon dioxide and hydrogen into methane, a greenhouse gas 25 times more potent than CO2. Establishing methane-producing colonies across Mars could create powerful atmospheric warming within decades. Fluorocarbon gas production offers the most efficient greenhouse warming per molecule. Perfluorocarbons remain stable in atmospheres for thousands of years and trap heat thousands of times more effectively than carbon dioxide. Chemical plants powered by nuclear reactors could manufacture these super greenhouse gases using Martian atmospheric CO2 and imported fluorine. Computer models suggest that releasing mere tons of these compounds annually could trigger significant atmospheric warming. The timeline for atmospheric modification depends heavily on the methods employed and resources committed. Conservative estimates suggest that sustained greenhouse gas production could increase atmospheric pressure by 10% within 50 years, potentially allowing liquid water to exist in equatorial regions during summer months. More aggressive approaches involving multiple simultaneous strategies might achieve breathable atmospheric pressure within 2 to 3 centuries. However, atmospheric thickening faces fundamental limitations with current technology. Mars's weak magnetic field means that any thickened atmosphere would gradually escape to space over millions of years, though this timeline exceeds human civilization's current planning horizons. Solar wind continues stripping away atmospheric particles, requiring continuous replacement to maintain artificially thickened conditions. Oxygen production represents a separate challenge requiring different approaches. The MOXIE experiment aboard NASA's Perseverance rover has successfully demonstrated oxygen extraction from Martian atmosphere, producing small quantities suitable for rocket fuel and life support. Scaling this technology to planetary levels would require enormous industrial infrastructure powered by nuclear reactors or extensive solar panel arrays. Atmospheric chemistry must be carefully balanced to avoid toxic conditions. Current Martian atmosphere contains trace amounts of carbon monoxide and other compounds harmful to humans. Any terraforming effort must ensure that atmospheric modification produces breathable air rather than simply thicker poison. This requires sophisticated atmospheric modeling and gradual introduction of oxygen-producing organisms. The engineering challenges are immense, but not insurmountable with current scientific understanding and rapidly advancing space technology. Atmospheric modification represents the foundation upon which all other terraforming efforts depend, making it the critical first step in transforming Mars into humanity's second home. Creating sustainable water cycles on Mars represents both the most crucial and most achievable aspect of terraforming with current technology. The red planet harbors enormous quantities of water ice, enough to cover the entire surface in a global ocean over 100 feet deep if completely melted. Unlocking these frozen reserves and establishing Earth-like water cycles could transform Mars within decades rather than centuries. The Mars Reconnaissance Orbiter has mapped extensive subsurface ice deposits across mid-latitude regions, with some formations beginning just inches below the surface. These ice tables contain pure water ice mixed with dust, representing easily accessible reserves for future colonization efforts. The Phoenix lander directly sampled subsurface ice in 2008, confirming its presence and purity in polar regions. Current drilling technology could access these water reserves immediately upon human arrival. Terrestrial ice drilling, equipment modified for Martian conditions, could extract thousands of gallons daily from known ice deposits. NASA's Resource Prospector mission concept demonstrates autonomous robotic mining of subsurface volatiles, while private companies develop ice extraction systems for lunar applications that could be adapted for Mars. Melting planetary ice reserves requires substantial energy input, but nuclear reactor technology developed for space applications could provide the necessary power. Small modular reactors, currently under development by multiple companies, could generate megawatts of continuous power suitable for large-scale ice melting operations. Concentrated solar power systems using lightweight mirrors could supplement nuclear power in equatorial regions. Establishing sustainable water cycles depends critically on atmospheric pressure increases achieved through greenhouse gas release. At current atmospheric pressure, liquid water immediately boils on Mars's surface, except in the deepest valleys. However, modest pressure increases from atmospheric thickening would allow liquid water to exist stably across much of the planet's surface, enabling precipitation cycles and weather systems. The magnetic field problem presents a more complex engineering challenge. Mars lost its global magnetic field over 4 billion years ago, allowing solar wind to strip away its atmosphere and break down water molecules into hydrogen and oxygen that escape to space. Any terraforming effort must address this fundamental issue to maintain artificially thickened atmospheres and protect surface water from continued destruction. Artificial magnetosphere generation offers a promising solution using current electromagnetic technology. NASA scientists have proposed placing magnetic field generators at Mars's L1 Lagrange point, the gravitational balance point between Mars and the Sun. A magnetic dipole field of modest strength at this location could deflect solar wind around Mars, creating a protective magnetosphere similar to Earth's natural field. The technical requirements for artificial magnetosphere generation are surprisingly modest. Computer simulations suggest that a magnetic field strength of just 2 Tesla, achievable with current superconducting electromagnet technology, positioned at the L1 point, could effectively shield Mars's entire atmosphere. The required power consumption equals approximately 1 nuclear power plant, well within current space reactor capabilities. Alternative magnetic field approaches include surface-based magnetic installations or orbital magnetic satellites. Networks of electromagnetic generators placed across Mars's surface could create regional magnetic protection for specific areas, allowing localized terraforming efforts while global magnetic field technology develops. This distributed approach might prove more reliable and easier to maintain than single-point solutions. Water cycle establishment accelerates once liquid water becomes stable on the surface. Martian temperature variations and seasonal changes would naturally drive evaporation and precipitation cycles. Seeding clouds with appropriate nucleation particles could enhance precipitation in targeted regions, gradually establishing river systems, lakes, and eventually inland seas. The interaction between water cycles and atmospheric development creates positive feedback loops that accelerate terraforming progress. Increased atmospheric pressure allows more stable liquid water, which increases atmospheric humidity, which enhances greenhouse warming, which further increases pressure and temperature. These cascading effects could transform Mars' environment more rapidly than linear projections suggest. Transforming Mars' toxic regolith into life-sustaining soil represents one of terraforming's most complex challenges, requiring the removal of deadly perchlorites while introducing Earth's microscopic ecosystem builders. Current biotechnology and soil science offer promising pathways to accomplish this planetary-scale remediation, though the timeline spans decades and requires careful orchestration of biological and chemical processes. Martian soil contains 4 to 20 times higher perchlorate concentrations than the most contaminated sites on Earth. These chlorine-based compounds destroy organic molecules and prove lethal to most terrestrial life forms. The Phoenix lander first detected perchlorates in 2008, while subsequent missions confirmed their global distribution across Mars' surface. Any terraforming attempt must neutralize these compounds before introducing Earth organisms. Perchlorate remediation technology already exists in terrestrial applications for cleaning contaminated groundwater and military sites. Biological reduction. Using specialized bacteria offers the most sustainable approach for planetary-scale treatment. Perchlorate-reducing bacteria such as Dichloromonas and Azospira naturally break down these compounds into harmless chloride and oxygen, processes that could be adapted for Martian conditions. Current genetic engineering techniques could enhance perchlorate-reducing bacteria for Mars' extreme environment. CRISPR gene editing allows precise modifications to improve radiation resistance, temperature tolerance, and survival in low-pressure conditions. Laboratory experiments have already demonstrated enhanced microbial survival in simulated Martian environments, suggesting that appropriately modified organisms could survive and reproduce in actual Martian conditions. Soil microbiome establishment requires introducing Earth's essential soil organisms in carefully planned sequences. Nitrogen-fixing bacteria must establish first, converting atmospheric nitrogen into forms usable by plants. Decomposer organisms follow, breaking down organic matter and cycling nutrients. Finally, symbiotic root bacteria and fungi create the complex soil ecosystems necessary for advanced plant growth. The Mars Sample Return mission, scheduled for the late 2020s, will determine whether indigenous Martian microorganisms exist and whether they're compatible with Earth life. Discovering native Mars life would complicate terraforming efforts, but might provide organisms already adapted to Martian conditions that could be genetically modified for soil improvement rather than introducing purely Earth-based life. Biocontainment. Technology ensures that introduced organisms remain controllable and don't develop in unexpected ways. Current synthetic biology includes genetic kill switches that prevent organisms from surviving without specific chemical supplements. These safeguards could prevent runaway biological processes while allowing controlled ecosystem development across targeted regions of Mars. Hydroponic and aeroponic food production systems offer immediate solutions for human nutrition while soil development progresses. NASA's vegetable production system has successfully grown crops aboard the International Space Station, demonstrating that space-based agriculture can produce fresh food using minimal resources. Scaling these systems to planetary applications could support large human populations during the centuries-long soil development process. Atmospheric nitrogen fixation becomes crucial as biological systems develop. Earth's atmosphere contains 78% nitrogen, while Mars contains only 2.7%. Biological nitrogen fixation by specialized bacteria could gradually increase atmospheric nitrogen content, though this process requires millennia to achieve Earth-like concentrations. Industrial nitrogen production might accelerate this process using Martian atmospheric components. Biodome technology allows controlled ecosystem development in protected environments, while planetary conditions gradually improve. These enclosed systems could maintain Earth-like atmospheric pressure and composition, enabling advanced agriculture and ecosystem testing before full planetary release. Current biodome experiments, including the Eden Project and Biosphere 2, provide valuable experience for designing Martian ecological systems. The integration of soil development with atmospheric and water cycle engineering creates synergistic effects that accelerate overall terraforming progress. Healthy soil ecosystems contribute to atmospheric composition through plant respiration and soil gas exchange. Root systems help retain water and prevent erosion, supporting stable hydrological cycles. These interconnected processes suggest that biological terraforming might proceed more rapidly than individual component analyses predict. Transforming Mars into a habitable world represents the most expensive undertaking in human history, with costs potentially exceeding the gross domestic product of entire nations over multiple centuries. Yet recent developments in space technology, private space investment, and resource utilization suggest that Mars terraforming might become economically feasible within the lifetimes of people alive today, fundamentally altering humanity's relationship with planetary resources and space colonization. Conservative cost estimates for Mars terraforming range from $500 billion to $50 trillion, depending on the scope and timeline of transformation efforts. These figures encompass transportation infrastructure, atmospheric modification systems, biological introduction programs, and support systems for human populations throughout the process. However, such estimates fail to account for technological advancement, economies of scale, and resource utilization that could dramatically reduce actual expenses. SpaceX's Starship development has revolutionized space transportation economics, targeting cargo delivery costs below $100 per kilogram to Mars. This represents a 1,000-fold reduction from current space transportation expenses, making large-scale infrastructure deployment economically viable. If achieved, these transportation costs would enable shipping millions of tons of equipment and materials necessary for planetary engineering projects. In-situ resource utilization offers the most promising pathway for reducing terraforming costs. Mars contains all raw materials necessary for construction, fuel production, and life support systems. Iron ore, aluminum, silicon, and other essential elements exist in Martian regolith, while subsurface water provides hydrogen and oxygen for rocket fuel. Developing Martian manufacturing capabilities could eliminate the need to transport most materials from Earth. Robotic manufacturing systems could establish production capabilities before human arrival, dramatically reducing infrastructure costs. Current 3D printing technology can produce complex structures using local materials, while advances in robotic assembly enable autonomous construction of large facilities. These systems could prepare extensive infrastructure for human colonization, while operating autonomously for years without direct supervision. The economic timeline for Mars terraforming spans multiple generations, requiring investment strategies that transcend typical business planning horizons. Government space agencies provide the most likely source of initial funding, as demonstrated by NASA's multi-decade Mars exploration programs and International Space Station partnerships. However, private investment increasingly drives space technology development, suggesting that commercial interests might eventually fund terraforming efforts. Resource extraction from Mars could eventually generate enormous economic returns that justify terraforming investments. Rare earth elements, platinum group metals, and other valuable materials exist on Mars without the environmental constraints that limit Earth-based mining. A single metallic asteroid contains more platinum than has ever been mined on Earth, suggesting that space-based resource extraction could become extraordinarily profitable. Tourism and real estate development represent additional economic drivers for Mars terraforming. Earth's ultra-wealthy already spend millions for brief space flights, suggesting substantial demand for extended Mars experiences. As terraforming progresses and Mars becomes more habitable, real estate values could reach extraordinary levels, creating powerful economic incentives for continued planetary development efforts. Current technology limitations require significant advancement before full-scale terraforming becomes feasible. Atmospheric modification needs industrial-scale greenhouse gas production. Magnetic field generation requires space-based electromagnetic systems, and biological introduction demands sophisticated genetic engineering capabilities. However, all these technologies exist in early forms and are advancing rapidly through both government research and private development. The critical missing technology is sustainable closed-loop life support systems that can operate reliably for decades, without Earth-based resupply. Current International Space Station life support requires constant maintenance and regular component replacement from Earth. Mars terraforming demands systems that can operate autonomously while supporting thousands of people across centuries-long timescales. International cooperation could significantly reduce terraforming costs through shared technological development and resource pooling. The European Space Agency, China National Space Administration, and other major space agencies have expressed interest in Mars exploration and eventual human settlement. Coordinated international efforts could distribute costs while accelerating technological development through shared expertise and resources. The realistic timeline for beginning Mars terraforming extends from 2050 to 2070, assuming continued technological advancement and sustained political commitment. Initial efforts would focus on atmospheric modification and water extraction, laying foundations for more complex biological introduction programs in subsequent decades. Full transformation to Earth-like conditions might require 3 to 5 centuries, but substantial progress toward habitability could occur within human lifetimes. Mars terraforming represents humanity's first attempt at planetary engineering, establishing technologies and expertise that could transform multiple worlds throughout the solar system and beyond.